All right, welcome back. Hopefully you enjoyed that first section of chapter 11, and by that last learning check, hopefully you were feeling pretty good. And if that wasn't the case, hopefully you either reached out to me for some help or did some extra problems or a combination of the two. And all of us, I hope, are now ready to move on to the alkanes in chapter 11. Whereas last lecture we were talking toward the end about alkanes, but we were mostly focusing on the generic properties of organic compounds and what distinguishes inorganic from organic, the whole definition of organic chemistry. But now we're ready to zero in on those alkanes and learn more about what makes an alkane an alkane. So I already mentioned that the alkanes aren't the most important in terms of biological chemistry, but they are going to be relatively simple and straightforward, and that's why we saw in the previous lecture, we saw things like propane and ethane and methane brought up. So the alkanes, again, will help get your mind thinking about organic chemistry. They'll get you ready for the compounds of biological relevance, and they do have some biological activity. If you've pumped your share of gasoline, hopefully you've done so without dawdling and sniffing and all that, because some of the alkanes, like the components of gasoline, although it may not be so much the alkanes as some of the other components there, do have an association with increased risk for cancer. So they don't do any significant biological activity, although they can do some undesirable biological activity if you're overexposed to large amounts over a long period of time. All right, so the names of the alkanes. So naming in General Organic and Biochemistry 1, Chem 141 at SUNY Broome, it was relatively simple, I hope. It involved either, in the case of inorganic ionic substances, we had the metal and the nonmetal, and we worried about the Roman numerals if we had a variable oxidation state like a copper ion, for instance. We could have copper 2 chloride or copper 1 chloride, that sort of thing. And then we had the penta and the hepta and all of that stuff for the covalent compounds, things like SO2 was sulfur dioxide, and CO2 was carbon dioxide, and CO was carbon monoxide, all of that stuff. That was hopefully a relatively straightforward naming. When we deal with organic chemistry, the naming gets a lot more complicated. So, if you're struggling with naming, which unfortunately a lot of beginning students in organic chemistry do, don't just ignore it. Reach out to me, get some additional practice problems, let me know where you're having trouble, because the naming only gets worse. And that's probably not the best news, probably not the news you were hoping for, but it is relatively logical once you get the hang of it. So practice does make perfect here with naming alkanes and then alkenes, alkynes. All of the compounds are going to have, unfortunately, these relatively tough to learn at first, although very reliable naming conventions. The naming conventions are all determined by the IUPAC, the International Union of Pure and Applied Chemistry system, and they use a prefix to indicate the number of carbons in a chain. They all end in ane for the alkanes. That's why alkane itself ends in ane. So that's the dead giveaway. You're dealing with an alkane is the IUPAC name is going to end in ane, just like propane and methane and ethane did back in the previous lecture. All right, so things aren't too bad, right? I didn't mean to get you all anxious about naming. If we have a simple alkane, the naming is pretty simple. You just have to get beyond those first few names. So if we have one carbon, these are all straight chain alkanes, by the way. We'll talk about branching and things like that later on. But one carbon gets the prefix meth. So methane for the alkane. We already mentioned methanol in the previous lecture. So that's our generic prefix for a single carbon atom is meth. Eth for ethane or ethene or ethyne or ethanol or what have you. Eth is the prefix for two carbons. Prop is what we use for three carbons, and propane was our classic example of an organic compound in the previous lecture. Bute for butane. Butane lighters used to be more popular when more people smoked. It's good that people aren't smoking as much. We know that's bad for your health, but it makes butane a little less relevant because you don't see it as much anymore. But that's our last of the what I'll call quasi usual names. They're not typical Greek prefixes or Latin prefixes. They're just sort of, you got to learn these if you don't know them already. Once we get to 5, it gets very predictable. They're Greek prefixes by and large, although I think oct, known, and dec become more Roman, Latin-based prefixes. But whatever, you've probably seen them all before. That's what I'm trying to get at. So pent for 5 carbons, pentane's our example of the 5-carbon straight chain alkane. Hex for 6, hexane. Hept for 7, heptane. Then we switch. If 7 were in the Latin, it would be sept. It's hept, so be careful. We're Greek up through 7, and then we go Latin for 8, 9, 10. So oct for octane, which is the principal component of gasoline. None for nonane, 9 carbons, and then dec or decane for 10 carbons if we're talking about alkanes. So there we have it. Those first 4, as I said, can be a little problematic, so I can teach you what I learned back when I was a high school student. We said most elephants prefer buttered popcorn. At least it got you the first letter. You were on your own to distinguish propane from pentane, but it got you more than just sort of rote memorization. So if you want most elephants prefer buttered popcorn, go ahead and use it. Hopefully it'll help you until you can get down those first 4. 5 through 10 hopefully are a little more familiar, but I understand those first 4 can be troubling at first. All right, so just like we did last time, we've done a little bit of lecture. Now it's time to see how well you're understanding the material with a learning check. So this is 2 parts. In the first part, you're going to give the name for each of these compounds, A, B, C, off those condensed structural formulas. And then for number 2, you're going to write the condensed structural formula of pentane. Okay, so give me the names for those that I've represented here on the screen, and then you come up with the condensed structural formula for pentane. Pause the video here, please, while you do that work, and then once you're ready to check your work, start back up, and we'll see how you did. All right, so hopefully these gave you very little trouble. They're just the straight chain alkanes. Hopefully you caught on to that. You're just counting carbons, therefore, at this point. And for A with 2 carbons, that's ethane, right? Eth was our prefix for 2 carbons, and since these 2 carbons are saturated with hydrogens, they're alkanes, and therefore they're ethane in this example. The next one, now we've upped it to 3 carbons. You've seen this one before, right? This is propane. And finally, if you counted carefully, you should have ended up with 6 carbons here, which meant you're at hexane for C. Number 2 hopefully was just as easy for you. You had CH3s at the beginning and the end, and then because it's pentane, you need a total of 5 carbons. So that means you have 3 carbons in the middle because they've already got 2 bonds to carbon, right? 1 bond to the carbon before and 1 bond to the carbon after. They only have 2 bonds left for hydrogen, so the central carbons are CH2s, the terminal carbons are CH3s to give you that overall condensed structural formula for pentane. If you struggled with either number 1 or number 2 or both here in the learning check, please do reach out for some help or at least try some additional practice problems on your own to help get the hang of it. And certainly you'll want to be able to do the homework set questions that correspond to these concepts. So reach out to me for help if necessary, but hopefully things are going well and you're ready to move on. All right, so the structural formulas that you tend to see for alkanes can be written either expanded, where we show every single bond. That gets old fast because we're dealing with pretty long carbon chains pretty quickly into the course. We tend to use condensed structural formulas, or as you'll see in the next slide, we use even shorter hand notation for a lot of these things just for convenience sake. But you should be able to recognize whatever form I use, and hopefully you should be able to use whichever form is most convenient for you. Expanded tends to be nice when we're looking at every atom, especially if we wanted bond angles or something like that, but condensed works well in terms of being able to represent the groups quickly. So you see, instead of the C with the 3 bonds to H's, just representing that as a CH3 group is much more convenient. Or the C with an H bond above and below, just having CH2 in one of those middle groups, like our propane example from the learning check you just completed. It's much more convenient to have it condensed like that. So sometimes, if I specify for expanded, then you'd want expanded. If I specify for condensed, then use condensed. But oftentimes I don't specify, and I would think probably condensed is the more convenient one to go to, but expanded isn't a bad idea while you're still getting the hang of drawing all these C's and H's and figuring out where they are in three-dimensional space. Now, once you get the hang of all that, these line bond formulas, or skeletal formulas as they're more commonly known, get to be very nice. They're very convenient. Each carbon has a tetrahedral arrangement in the alkanes that we're focusing on now. So the order of the atoms is not a straight line, but a zigzag pattern to represent that idea of a bond angle. In the case of the alkanes, it should be roughly a 109.5 degree bond angle, but at least a zigzag line shows that it's not a straight line. It also allows us to know that each time we zig or zag, we have a new carbon atom. So if we look here, this is a really quick way to represent heptane, which you could do with an either expanded or a condensed structural formula, but that takes time to draw in the C's and H's in the case of an expanded one, or to just write out CH3, CH2, CH2, so on and so forth for the condensed is still time consuming. These skeletal formulas you can draw very, very quickly. They do take a little getting used to, so hopefully, maybe within a week or so, you'll be to the point where you're confidently drawing these, especially if you're doing the outside practice. You should for this course, but every point there is a carbon atom. So the terminus at the beginning and the end is a CH3 group, and then the peaks there, or the troughs where we have a point between two lines, that's a CH2 group. So this is a quick way to draw heptane. We have 7 starting at the left to right. Every either the end or every time we make a bend, we have a new carbon atom. So that's where I hope you'll all be very, very soon, but I can understand if this is your first time seeing it, it does take a little getting used to, but do practice and try to get there, because these are the most convenient way to represent organic structures, and they're just fun to do. If for no other reason than you can do something that very few people in the world can do. Most people, this is a bunch of nonsense, but now this is organic chemistry. All right, so here we see hexane represented in a number of different ways by alkane name, right? Hexane, that should trigger in your mind the molecular formula C6H14. The ball and stick model there gives a little idea of the three-dimensional structure. Hopefully you have a molecular modeling kit. I didn't require it, because if I required it, then I'd have to require a specific one, and it's fairly expensive. But if you can get your hands on a used one, it's very, very convenient. And if you want to send me an email, ask for more information about what ones I might recommend. There's a lot of good types out there, and they're all different and have their own strengths and weaknesses, but used molecular modeling kit is not a bad investment for a course like this, where you're going to be doing a lot of this, and since we're in the online environment, we can't sit down in the lab and work with actual modeling kits that I could provide. But if you can pick up a cheap used modeling kit, it will help you tremendously, in my opinion, to understand the structural formula. The expanded structural formula, as we said, where you're drawing in every C to H or C bond here in the alkanes with a dash. Condensed structural formulas, you've only got dashes to join groups of atoms, where you're not showing every CH bond. The skeletal formula, where we really want to be, because it's the most convenient and the most popular type. If you go on in chemistry or biochemistry or medicine, you're likely to see these skeletal formulas almost exclusively for organic compounds. If you've ever actually taken out that insert that comes with a prescription drug, it'll show oftentimes the skeletal formula, or at least something that uses a lot of skeletal formula to it. There might be some other groups in there that they don't necessarily obey all the chemist rules for skeletal formulas, but you'll see because a lot of those compounds are pretty complex, they tend to abbreviate using the skeletal formula. I've probably made the point a couple of times already in the course, but the rotation around a CC single bond or any single bond is free rotation. So what that means is the components of that bond can rotate freely around each other to give different relative structural arrangements called conformations. So sometimes, for instance, the methyl groups here, the CH3 groups line up, and sometimes they are opposite to one another, and that does have a difference in energy, because if you think about 3D structures, and if you have one of those modeling kits I just mentioned, you can build these things and see that in the real world, where there aren't sticks between atoms, where they're actually sharing their outermost electron densities, there's going to be some less give, I guess, or some more what we call constraints when you have both the methyl groups up where they can interact, and because they're electron groups, they're going to repel. Whereas if they're opposite each other, now you've got less steric hindrance, is the phrase we often use in organic chemistry. So they're less sterically hindered. It's a better conformation in terms of energetics. It's not so much repulsion between these large groups. Again, methyl groups aren't that large, but we get into much larger groups and we can have real problems with steric hindrance if we happen to be in a conformation that has big groups around each other. We tend to prefer to have the groups opposite each other, like you see on the right-hand side. One of the problems that free rotation brings is that beginning students have a little bit of trouble understanding what's really different and what's just a free rotation sort of consequence. So if we look at the expanded structural formula for butane, that's pretty clear if we keep it flat, right? It looks like everything's flat. Of course, that's not true, but that's how it looks on two-dimensional paper. Condensed structural formulas, you can do things that might make it look different. So we have it sort of in a straight chain there in the far left top. Then we have it where it's almost a square. If we were to connect those two CH3 groups the way we've drawn it there, it looks like it's a different substance. If we make it more of a ziggy chain, like in the third case, or a down instead of horizontal line, all these are just manipulations of that free rotation. There's nothing different about any of them. The skeletal formula, there's relatively little we can do there, although we can, instead of starting with a point down and drawing a line up, we could start with a point up and draw a line down. So that's why skeletal formulas are preferred, because there's not as much confusion usually, but just be careful. Those are all representations of butane. There's probably some other permutation you've come up with on your own. As long as it's just those groups joined in that way, it is butane. No matter how you choose to draw those 4 carbon groups, it's still butane. It's just a consequence of free rotation around those single bonds. Okay, so here's some advice to help limit confusion on those structural representations. If we're drawing structural formulas of something like pentane, H12 rather, sorry, it has 5 carbon atoms connected to each other and to those hydrogen atoms with single bonds to give each carbon 4 bonds. So the terminal carbon groups will have 3 bonds to hydrogen. The carbon groups inside the molecule will have just 2 bonds to hydrogen. So in a condensed structural formula, carbon atoms on each end get written as CH3 and then a dash to indicate they're joined to another carbon. In the middle, they're written as the CH2s for the reasons I just described. If you're doing a skeletal formula where it's a zigzag line, the ends represent those CH3 groups, the corners represent those CH2 groups if we're dealing with just a straight chain saturated alkane. Okay, well, that's what we're talking about right now, so we'll be good, but we will make it more complicated as we move in to the alkenes in the next chapter and so on and so forth. So for now, these are the rules. Let's build on these baby steps and then move into the more complicated things later on in the semester. All right, so if we look, that expanded structural formula, it's the easiest in terms of having the least places for confusion, but it's also the most time consuming to draw out. So the condensed structural formulas are more convenient. They do take less time, but they can also have the problems where depending on how you choose to make them look on paper, you might confuse yourself into thinking you've got different molecules when you've just drawn different ways of representing the same thing. Finally, where we hope to be soon, the skeletal formula, that's the best, the simplest, but it does require some chemical savvy, right? You've got to get used to that idea of each of those terminal points being a CH3 group, each of those bends being a CH2 group at the corner. All right, let's pause here for a learning check, see how you're doing, at least with the idea of condensed structural formulas and molecular formulas and names. So here in this learning check, for number 1, we have we are asked to draw the condensed structural formula of this substance that I won't name because that's one of your later jobs here, but you're going to take this expanded structural formula and condense it. You're also going to give me the molecular formula and finally the name of this substance. All right, so pause the video here while you complete those tasks. Start us back up once you're ready to check your work. Okay, hopefully you did very well here. It didn't take you very long, I hope, to condense that structural formula. This is probably the way you've shown it, but again, if you have, a CH3 group going down from that first CH2 group or up or whatever we talked about earlier, as long as it has a CH3 connected to a CH2, connected to another CH2, connected to another CH2, another CH2, and then finally connected to a CH3, then you've got the right substance. The molecular formula, if we count all the carbons and hydrogens, it should be C6H14, and the name for that substance is hexane, N-hexane, as we'll find out later on. But for now, hexane because it's 6 carbons, saturated alkane. All right, hopefully that went well. If it did not go so well, whichever part caused you trouble, please do try some additional practice problems or reach out to me for some guidance, and hopefully we'll get that squared away quickly. All right, here's a follow-up learning check just to make sure you're good with the condensed structural formulas. Ethane A and heptane B, probably first you'll want to draw the expanded structural formula and then the condensed structural formula for those substances. If you can go right into the condensed, great. If you could go ahead and give me the skeletal formula, wonderful, although I don't have those on the answer slide. But again, hopefully at least getting the condensed structural formula for these two won't be too much trouble. So pause the video here while you complete that task, start it back up when you're ready to check that work. All right, so ethane was a nice easy one, right? The condensed structural formula is the same as the expanded structural formula in that case because it's just 2 carbon groups joined together, so CH3 groups in this example. And heptane's a little more complicated. Hopefully you were able to find that heptane is 7, right? Hept is 7 carbons, so a carbon to start and end is a CH3 group, and then those 5 carbon groups in the middle are CH2 groups. So hopefully you did that. And I did misspeak earlier. It's slightly different for the expanded. For ethane, you'd show each of those CH bonds separately, but it wasn't too much work to get down from expanded to the condensed for ethane. For heptane, it was quite a few more bonds to condense. So hopefully they both went well. If not, please do reach out. Otherwise, we'll move on to a new topic. All right, so we've talked so far about straight chain alkanes, and what I mean by that is where you have a CH3 group to start, a CH3 group to end, and then if you have any other carbon atoms in between, they were CH2 groups. For those who are paying close attention, what that always gave was a formula where it was C to the N and then H to the 2N plus 2. What do I mean by that? Well, I mean if you had ethane, for instance, you had C2H6. So C sub N, N is 2 there, and then H sub 2N plus 2. So 2 times 2 is 4 plus 2 is 6. And it worked out well all the way up to decane would be C10H22, right? Once we get to cycloalkanes, that's not always true because those two terminal carbon groups now link together to make a chain, a cycle, a ring. So cycloalkanes are carbon rings, and these cycloalkanes have 2 fewer hydrogen atoms than straight chain alkanes, because instead of having those CH3 groups to start and end, you take away an H from each of those groups, and then you can join the carbon atoms together. This is, again, where having a modeling kit would be very convenient to prove this to yourself, right? Being a good scientist means you have to see the evidence for yourself. The other way that they're different than the alkanes we've talked about so far is that they use the prefix cyclo just to distinguish them. So they have that different formula, and they have that cyclo prefix that they should stick out. Also, if we show them graphically, they have a ring. So that's another way that they would stick out. But sometimes if you're just dealing with a molecular formula, you might not notice that there's a ring if you don't know what to look for. All right, so Skeletal formulas, I've already come out and as a big proponent of skeletal formulas. They are very nice for rings as well, and that's one of the reasons you tend to see them a lot for rings, because they're convenient. But you can also have a ball and stick model or a condensed structural formula that you try to make into a ring. The name gives it all away, right? If you have that cyclo prefix, you know you're dealing with some sort of ring. So you have to have enough atoms, first of all, to make a ring. So you can't really have cycloethane or cyclomethane because you can't get 2 carbons or 1 carbon to make a ring. The smallest rings we can make are 3 rings, so cyclopropane, and even those are not terribly stable. There's a lot of ring strain there because you've got sort of a triangle pattern, right? 60-degree bond angles, and we want 109.5, so that's not anywhere near ideal. Once you move up to a 4-membered ring like cyclobutane, you can see it's already puckered. That's what the ball and stick model picture is trying to show you. And if you have the modeling kits and try to build this thing, it's not going to make a nice planar square. It's going to have some buckling to it because obviously that 90-degree bond angle is not ideal either. So we're trying to expand that to the 109.5. Once we get to the cyclopentane, now things are a little better, right? The bond angle is closer to that 109.5. And then finally, the cyclohexane, there tends to be puckering as well that you can't see too well in this picture, but if you build it for yourself, cyclohexane actually gives a very nice ring without too much strain at all because of the way that you can have the bonds go up and down instead of just trying to keep them straight into one plane. But as you see, the skeletal formula, that's great. It's a triangle, a square, a pentagon, and a hexagon. We'll see loads and loads of hexagons, especially in pentagons, as we move into biological chemistry. But these are really neat, really fun to draw, very important biologically speaking once we get them substituted. But as cycloalkanes, they're not terribly interesting for biological applications, although they are really neat and interesting just for the sake of chemistry. All right, so as a follow-up to our short discussion here about rings, the cycloalkanes, let's follow up here with this learning check. The molecule testosterone contains 4 carbon rings. Answer the following questions about the molecule. Name each of the cycloalkanes that can be found in this molecule. So just be careful that very first ring, the one to the lowest left, it has that second line. That's not an error. That's a double bond. We'll talk about that when we get to the alkanes. Alkenes. This is alkanes in Chapter 11. Chapter 12, we'll talk about alkenes. So exclude that, and then the remaining 3 you can classify using our brief discussion of the cycloalkanes. Pause the video here while you do that, and we'll start back up as soon as you're ready to check your work. Okay, it might have been a little early for such a complicated question, but hopefully you did pretty well and you could identify at least the 2 different types. At the very far left, that last ring, because of that double bond, is technically a cyclohexene, so I didn't include that. We'll talk about the alkenes in the next chapter, but if we're looking at the next 2 rings, they're both fused together there as cyclohexane rings, right, because they look like our classic hexagon shape. And then finally, the last ring we have is a cyclopentane ring. So there we have it, our cyclohexanes and cyclopentane as the rings we should have been able to identify. And then, of course, if you wanted to call that cyclohexene, that very first one, a cyclohexane. Since it's still early on, I wouldn't have deducted for that small error, but that would be, again, technically incorrect because of the double bond. All right, that's what that second line at the bottom right would indicate. So hopefully you did well, and hopefully at least if you didn't do so well because it was too early for you to get that down, you understand better now what we're talking about. Let's try one more learning check before we leave this section of Chapter 11. It's asking you this time to name the following alkanes, and so we've got everything from straight chain to cyclo. Just remember to include that prefix. If you are dealing with a ring, it needs the cyclo prefix. So stop the video here while you complete these 4 naming tasks, and then once you're ready to check your work, start us back up and we'll see how you did. All right, so that first example, letter A there, that's a 4-carbon chain, saturated alkane, and because it is 4 carbons, that's butane. Hopefully you did that one just fine. B is still 4 carbons, right? Each of those corners is a carbon atom, along with enough hydrogens to saturate it for the alkanes, rather. But because it is in a ring, it's now a cyclobutane. And if we compared the molecular formulas for A and B, A would be C4H10, whereas B would be C4H8 for the reasons we talked about earlier in this lecture. C, now we have 8 carbons total, and it's all in a straight chain, so we call that octane, right? Oct being the prefix for 8. And then finally, D is our classic hexagon. Because it is a ring, we need the cyclo prefix. Because it is 6 carbons in the ring, it gets the hex. And because it's just carbons and hydrogens all saturated, it's an alkane, so it gets the ANE ending. So hopefully this topic on not only the alkanes but also now the cycloalkanes is coming together for you. If you're struggling, please do try some additional practice problems. Reach out to me for some guidance if necessary, but hopefully you're still doing well and you're having fun with getting close to perfection on these structural formulas, especially the skeletal formula, which we have here for the cyclobutane and cyclohexane. Those are going to be important as we move on, so please do get some practice in with those if you haven't already. Okay, otherwise, if things are going well, I'll see you for the next section of Chapter 11.